I'm going to show one kind of interesting thing, I hope. Um, Oops, I went too far. Here we are on the other modes. So this data set here, um, I have to go to all files, and I'm going to pull up this data set here. This is a Raman data set from a Hariba text output. Hopefully when I open this, it won't yell, but it does recognize that it is a Hariba data format, opens it up and gives you a total sum of all the Raman spectra right here. Okay, well, that's kind of boring. We want to see a little bit more about information here. So if I go to MCA spectra here, I can define the MCA file. But if you notice here, it added a Raman HDF file. This is now all the extracted Raman data into a SAMS format of MCA type data. We'll open that up. We are not going to do an alternate coordinate system, so go away there. And I am going to view this in Spectrum. And I do want this in the values in the MCA file. And so now if I say view MCA, and if I double click on a point over here, let's say that one, I now get a lovely Raman spectra from that particular pixel. And this is now in proper Ramanesque units. Now we could fully background subtract this as well. I'm going to cheat a little bit and just show this next bit right here. We're going to take a look at this particular peak here around six. Well, I'm going to do two things. I'll do a few things. We are going to study this peak here in a minute. But I may want to go like this total Raman was great, but it really doesn't tell me much about my sample. So why don't we try to figure out what's in there? So I'm going to go to Analyze, and we're going to do PCA analysis, but rather than doing the old-fashioned way we did it on the channel data, we're going to do it on the full Raman hypercube data. So I'm going to say PCA analysis on MCAs, and it brings up this little screen right here. And here we even have PCA type. So we can do the standard PCA, but again, that gives us negative values and positive values and things that don't make a lot of physical sense. So I'm going to do a non-negative matrix factorization, so NMF. This makes every component positive, so they all have somewhat more meaningful information than a true PCA. When you're doing this with channel data, I've always found that keep my number of components smaller works better, because otherwise you'll find all kinds of weird stuff. But since my data set is 4,000 bins wide, if I tell by default it's going to pick out 10 components as a good start, that will be just fine for NMF. And so we'll say that's fine. I'm just going to say do analysis. Oh, okay, fine. So define the MCA file. Fine. Now do the analysis. And here we're going through. It's doing it. It finished it, and there's my components. And ideally, in a perfect world, they look like, okay, some backgroundy things, some peaky things. There's some peaky things, peaky things. Those look like peaky things. Some ugly scattery things, right? Really ugly scattery things. Kind of interesting, kind of interesting. So we have a good set of things we can say that were picked up there. I'm going to double click on all these to select them. This is one thing I really notice. I do need a select all button to prevent my carpal tunnel problems. It's funny, I never used to use this with XRF data, since the XRF data is pretty orthogonal as it is, and isn't very helpful. But it turns out this is really helpful for all the other infrared type modalities and everything else. So it's coming back into being cool again. And then we tell it to save all the vectors to data. Oh, let me Aaron type. Let's just say save then. And so now we can see where those are located. Component 1, 2, 3, there's, that looks beautiful. 4, 5, 6, 7, 8, so on. This is gonna be a really interesting one that I'm gonna get back to, and along with that one. So if we look at those, that's 3 and 10, for instance, right? If I look at what 3 and 10 look like, I have 3 and 10. They're really similar. There's actually a little bit of a shift in here. Like, what's the heck's going on here? Let's look at this peak around here again. So we have that one. Oops, of course it zooms out of me. And this one. This one's a little cleaner. So 316 in the bin position. And 318 in the bin position. So there's a little shift of that Raman peak over to a higher wave number. So we want to kind of maybe take a look at that. And this is just, again, this is in the components here. You can see how this is probably just a peak adding over to the corner, a little bit of a lower number here, creating that shift over. If you want to save all these values, you can say save components to file. And it'll save all of these spectra to file. So you can go back and look at them later and figure out, remember what component 10 looks like, and 8 and so on. I have half a mind one day to combine this to like a Raman library and actually try to do some peak finding and peak matching, at least for the mineral people. Haven't quite got there yet. So okay, let's see what we can do with this. So there's a little bit of some weird peakiness going on maybe. And so I'm gonna take component 3 and 10. See how they're kind of related to each other a little bit too? You see how that one's, they're kind of almost inversely proportional. This actually is diopside as a mineral, as it turns out. And there's some interesting things with the diopside going on there. So I'm going to do a quick thing where we take in, where are we? Math. I'm going to take component 3, add that to component 10, and call this D for diopside. I don't feel like typing the whole thing out. Okay. So we have, this is the area that has all kinds of cool peaks that we are interested in, particularly at that 660 or so wave numbers. There's all the areas that have been highlighted now in this new channel. We're going to do our favorite bits of going to process and thresholding. And we're going to find all the areas that have this particular cool peak in it. So if I take our D channel, do some inverse binary thresholding, lower this to some hopefully relevant value, and look at that, that looks perfect. We'll go with that. So that's our areas that are represented by diopside on the map that have the peak that we're hopefully interested in. We're going to save that channel. And now we'll see if this still works because it's been a while. I'm going to be on the D threshold channel under MCA spectra. I hope it's in, nope, it's not in there. Oh, it's in here, I think. Yeah. Let's see if it's in here. Yeah, here we go. Okay. I will make a note that if you do want to do full background subtraction-y things, you have a whole thing in FTIR support, you can convert transmitted data to absorbance data and use the octaves package here to do normalizations and saving your data again. I know we're all a little fried, so I won't go into all of that process. But what is cool is we're going to see if we can actually characterize this interesting shift here. Because if you remember, we had that one component down here. And if I go at the top of the map, it just shifts a little bit over. So how can we quantify that? We're going to go to fit spectral peak data there. We're going to do pseudo Voigt calculations here. I think it's this one. We need to tell it, we don't want to fit Raman peaks where they don't exist. So we're going to use the D threshold mask to only fit those regions. And we're going to come back here and tell it to fit the peak in between. Did I tell it the right one? I think I wanted spectral feet. Well, we'll see how it works. We'll say about what? 600 to 750. And this is our diopside. It's not going to like me because I think I fit this in bins and not in wave numbers. This is going to take far too long. I did the wrong thing. I believe we wanted the active, not the other one. What I will say is it looks like this. Yes, we know. No, don't need to search. I am going to cheat. I'll just open up the process data that I did before. And just because in the interest of time, what is it called? Yeah. And so we can see that it fits the intensity of the peaks there. Let's see. The peak height. Is this the better one? Yeah, there we go. The intensity, the peak height, the full width half max, so how wide that peak is, and it picks out the position here. While this looks all the same here, it is, well, because it's scaled a little bit weird. Let's see how I did this before here. You have to say, oh yeah. So it's 664 at the bottom here, and about 667 at the top. So it has about a 4 wave number shift. And if I do something like, if I set the maximum scale here, to be, it's not one giant monitor as it turns out. 668. Okay. Oh, I remember. Sorry. I have a hard time plotting these as a range, as it turns out. So the easiest thing to do to get a good look at this is to do math. I think this is actually an error in my plotting routine, but we won't really talk about that right now. I'm going to take the position of that peak. I'm going to subtract the 640 or so off of that. And here you begin to see it a little bit better. See how it begins to change color at the top there, right? Let's take another 10 wave numbers off of that. And that shows you the shift there between the low and the high. And so as you go, so the question is, what does this really mean, of course? There could be a Raman shift because the crystal orientation is changing, and we're getting a slightly different axis, or it could be a crystallinity effect as well in this case. That could also give a small shift on that as well. So obviously there would be some really cool things to be able to do, to go look in and maybe look at the spectra of the minerals in these cases, in these regions here, and see what other chemical differences might be happening. Or So this kind of begs to look at the X-ray data as well as the Raman data together and see how these things shift. And you can do this with any set of peaks. Actually do some fitting to see if there are shifts or changes in the data set. Integrate areas. Also use this for FTIR to look and again see if peaks are shifting or changing, or looking at integrating different areas and actually doing a proper peak fitting rather than just a binning on it too. So it'll fit the background out